This is Donna Nelson at the University of Oklahoma, taping another lecture for my organic chemistry class. So this will be the third lecture in the chapter 19 on aldehydes and ketones. So now you're going to see nitrogen nucleophiles. We covered the hydrolysis of acetals up here in section 5. We're going to see hydrolysis of imines and enamines, sulfur nucleophiles, and hydrogen nucleophiles in this lecture. And then we'll go on in the next lecture to carbon nucleophiles and some specialized reactions of aldehydes and ketones. So now let's look at nitrogen nucleophiles. This is under acidic conditions. An aldehyde or ketone will react with a primary amine to form an imine. And imine is a molecule that has a carbon-nitrogen double bond. So you can see that the carbon-oxygen double bond has been replaced by a carbon-nitrogen double bond, and nitrogen is still bearing the alkyl group that it was in the reactant. And this reaction requires acidic conditions in order to work. So let's look at the mechanism, and this mechanism will be sort of important to remember because there will be other mechanisms with nitrogen nucleophiles that will be very similar to this. So the first step is that the lone pair on nitrogen comes in to do a nucleophilic attack on the carbonyl. It comes in, that lone pair occupies the antibonding orbital of the pi bond, which is back here, so the nitrogen doesn't really come in from the side. A pair of electrons in the carbon-oxygen pi bond moves out onto oxygen, creating a negative charge on the oxygen. And nitrogen is bearing a positive charge because it used the lone pair to do the attack on oxygen. So notice overall this molecule is neutral, even though there's a negative charge on oxygen and a positive charge on nitrogen. So then the next step is for a proton transfer. So the lone pair, one of the lone pairs on oxygen does a nucleophilic attack on the proton, and so it becomes protonated, and then the conjugate base, a lone pair, will come down to deprotonate nitrogen and make nitrogen neutral. The pair of electrons in the nitrogen-hydrogen bond moves back onto nitrogen, satisfying the positive charge on nitrogen. So now we have this neutral molecule. And so remember, the goal here, when drawing a mechanism, you have to keep in mind the overall goal. The overall goal is to replace the carbon-oxygen double bond with the carbon-nitrogen double bond. And so you need to continually do things, do steps that will eliminate the oxygen. So this is going to be done by a succession of breaking bonds between carbon and oxygen. And in order to do that, you're going to have to repeatedly protonate oxygen and then break a bond. So now here we're going to protonate oxygen, and that will convert oxygen into a nice neutral leaving group. This will come off as water. And so then to facilitate the departure of water, a pair of electrons on nitrogen is donated in to form a carbon-nitrogen double bond. That this will be the pi bond that is forming. And as that forms, the pair of electrons in the carbon-oxygen bond moves out onto oxygen, satisfying the positive charge. And so then you see water leaving. You have a carbon-nitrogen double bond. You'll see later that these mechanistic steps will be present in other reactions. And so in some other mechanisms, the entire mechanism will be the same, except for this very last bit. You can see that a base comes in and deprotonates, removes a proton from nitrogen. And that gives you the imine, which is the product. Now here, even though it's under acidic condition, protonation of the carbonyl is not the first step of imine formation mechanism, it's believed. So the nitrogen nitrogen lone pair is protonated. Hydrochloric acid, of course, is very acidic. And so this consumes the catalyst and forms the ammonium ion. So the ammonium ion is actually the acid catalyst that you saw donate the proton up here. This is actually the ammonium ion that's donating the proton. But it's not acidic enough to actually protonate the carbonyl. So let's go back and look. It's not acidic enough to protonate the carbonyl, but it is acidic enough to protonate the oxide. For amine formation, the pH has to be right around 5, or the reaction is just too slow. So here's the rate of reaction. You can see increasing energy as the pH, or the increasing rate as the pH changes. So you can see that right around a pH of 5, the rate of the reaction is highest. Under acidic conditions, the aldehyde or ketone can react with a secondary amine, and here an amine is formed instead of an imine. So the vast majority of the steps are the same, except the last step. So let's look at this. Once again, let's go over the steps that are identical to the steps for imine formation. A lone pair on nitrogen comes down, occupies the antibonding orbital of the carbon-oxygen pi bond, facilitates cleavage of that pi bond. The pair of electrons in the pi bond moves out onto oxygen. Then the ammonium ion donates a proton to neutralize the negative charge on oxygen. A pair of electrons on oxygen does an attack on this proton, and so it picks up a proton. Now the conjugate base of that ammonium ion picks up a proton, it deprotonates the ammonium group, and a pair of electrons, the pair of electrons in the NH bond moves back onto nitrogen, satisfying the positive charge on nitrogen. Now you have this carbonyl amine formed, again, exactly the same as in the previous mechanism that we covered just a minute ago on the previous slide. Then the pair of electrons on oxygen comes in, picks up a proton from the ammonium ion. Once again, pair of electrons moves out onto nitrogen. So you have the protonated water here, which is a great leaving group. So this water is going to come off as a neutral molecule. The pair of electrons in the carbon-oxygen bond moves out onto oxygen, and the leaving group departs. A pair of electrons on nitrogen moves in to form a carbon-nitrogen pi bond, and that facilitates the departure of the leaving group. The carbon-nitrogen pi bond is formed just as before. This mechanism so far is exactly the same as in the previous slide, except in this case, nitrogen is not bearing a proton. You do not have the NH bond here. And so instead of the acid coming in and deprotonating, removing a proton from nitrogen, what happens is the acid comes in and deprotonates at the alpha position, at the alpha carbon, and so it removes a proton, the pair of electrons moves in and forms a carbon-carbon pi bond. Here, this is the pi bond of the enamine. So this is the ene of the enamine, and up here you can see the amine group. When this pi bond is formed, the pair of electrons in the pi bond of the carbon-nitrogen bond moves out onto nitrogen, satisfying the positive charge. So this reaction is the same all the way down to here. This mechanism is exactly the same all the way down to here. And it's just this last bit that is different, and that's because instead of having the proton removed from nitrogen, the proton is removed from the alpha position. So you can see this drawing emphasizes the difference between the two mechanisms. Here in this is just the last step of those two mechanisms. In the first mechanism that you saw, nitrogen is deprotonating, removing a proton from nitrogen. Here, nitrogen is deprotonating at the alpha position. And so you can see that here in the first mechanism, we have formation of the imine, and here we have formation of the enamine. So the mechanisms for formation of these two molecules are identical, except for just this last step. The Wolff-Kishner reduction is a two-step synthesis, and once again, this first step has a mechanism that is identical to the imine formation that you saw earlier. So we're not going to go over this a third time. Just go back to the first mechanism. Here you see the imine formation. Instead of having an alkyl group here, you've got another amino group. That's because here you started with hydrazine instead of a simple amine. So this other amino group is still here, and now we simply do an elimination reaction. So we're treated with base and heat, and the carbon-nitrogen pi bond can be replaced with two carbon-hydrogen bonds. So this is like an elimination. Let's look at this mechanism, the mechanism for this last step. So remember, this is under basic conditions. So the base comes in and deprotonates and leaves a second non-bonding pair on nitrogen. Then a non-bonding pair on nitrogen moves in, forms a double bond between nitrogen. So this forms a pi bond of the double bond. The pair of electrons in the carbon-nitrogen pi bond moves on to carbon. Now you have the non-bonding pair constituting the negative charge. This comes in and deprotonates water, regenerating the hydroxide. So now you have a nitrogen-nitrogen double bond. What you're going to form is a nitrogen-nitrogen triple bond, because that's gas, and that will make it an excellent leaving group. So what needs to be done now is the base comes in, removes a proton again, and this nitrogen-hydrogen bonding pair moves in and forms the triple bond. It moves in and forms, so first the proton is removed, then the pair of electrons on nitrogen moves in and forms the second pi bond of the nitrogen-nitrogen triple bond. Then the pair of electrons in the carbon-nitrogen bond moves back onto carbon as the nitrogen-nitrogen triple bond is formed, and so N2, molecular nitrogen, is expelled. This will be an excellent leaving group and pushing the equilibrium to forward to the product, because this gas is expelled, it's given off, and so you're not going to have an equilibrium after the nitrogen is removed from the reaction. So here we have the carbon atom has accepted this pair of electrons. It is bearing a negative charge. The pair of electrons, the non-bonding pair constituting that negative charge, comes in and deprotonates water, regenerating the base. And so then the product is formed. And so the overall reaction is that the carbon-oxygen and then carbon-nitrogen double bond is replaced by the carbon-nitrogen double bond, which is then replaced by two CH bonds. So this is a good way to replace, overall, it's a good way to replace the carbonyl with methylene. So there are many similarities all along the way, but one that must be emphasized is that under acidic conditions, you will always have compounds that are either neutral or positively charged. You will not have anions present under acidic conditions. So if you're drawing a mechanism, you never want to draw an anion if the reaction is taking place under acidic conditions. So hydrolysis of amines and enamines undergoes a very similar mechanism under acidic conditions. So it's simply the reverse of formation of the amine or enamine. Now for sulfur nucleophiles, you may remember in the last lecture I pointed out that sulfur is just below oxygen in the periodic table, and so remember we saw the formation of acetals and cyclic acetals with oxygen in these instead of sulfur. And so if one substitutes sulfur compounds instead of oxygen compounds, you might expect to be able to generate the corresponding sulfur products. And indeed, one does. It is possible. And so instead of acetals, thioacetals would be generated. And instead of cyclic acetals, one will generate cyclic thioacetals. So the mechanisms are exactly analogous. And so you can simply think just everything that you've learned about acetals, that's the corresponding oxygen compounds, also applies to thioacetals. So, except one difference is that the thioacetal can be reduced to the methylene by simply using Raney nickel. And so this is another method for reducing the ketone to the methylene. So notice that the previous mechanism, let's go back and just take a quick look at the previous mechanism. The previous mechanism for doing this was done under basic conditions. This removal of the carbonyl, substituting a methylene for the carbonyl, was done under basic conditions. And now we are removing the carbonyl. It's changed to the thioacetal under acidic conditions. So here acidic conditions would be needed for this route of changing the carbonyl to methylene. So another reaction, we're going to a totally different reaction now, and this is using hydrogen nucleophiles. So lithium aluminum hydride and sodium borohydride are both reducing agents, and remember that they are very similar in that they furnish H-. And so when H- is furnished, it's going to simply attack at the carbonyl carbon. The overall reaction here will be formation of the alcohol. And so here, this shows the mechanism. Lithium aluminum hydride, here is the aluminum hydride. You can simply think of this as H- doing an attack at the carbonyl carbon. And then once the oxide is formed, that can be neutralized, and the pair of electrons on oxygen will do an attack at a proton of water, and the alcohol product is formed. It's an analogous mechanism for sodium borohydride. The mechanism is analogous. So just think of both of those compounds as furnishing H-. When that reaction does occur, remember that, coming back here, remembering H- can come in either from the top or from the back side. And so both stereoisomers are possible. And so the product will be a racemic mixture because you will have an equal probability of H- entering from the front or the back because the molecule is symmetrical. So that takes care of the additional types of nucleophiles, and this then ends the third lecture for this chapter.